Pre-calculus. Let's see, we got Unit 2, Lesson 7. And yeah, this lesson is called Detective Zero, but it's all about like using the zero stuff that we've been doing over the past few days to decode and factor out some of these polynomials. In class, we had this problem where it's like we were given a fourth degree polynomial, and then we're also given some information in a table, and lo and behold, in that table, we found out that there was a 0 at 2. That means we go 1 unit, 2 units over. Now wait, it's definitely like hits that point. How do we know that there's a bounce there? Well, it says right here's the thing, is that we know the end behavior for this function is going to be like 1 up, 1 down. We don't know what the heck happens in between unless we combine this information, and it says f of x, the function, this red part that I'm drawing right here, the function, if I were to come in and squiggle in the rest of this polynomial function, is more than or equal to 0 on the y-axis, more than or equal to 0 for every value of x that we could ever put into it. So that means right as we're going through all the way here, it could hit 0 again. It could hit that 0 height again. But as we're looking at it and everything, like it's never going to dip below, so it's never going to go in this area. All right, so, and then we also had another bit of information here saying that there's at least one imaginary 0, which means that there's really 2 of them. That means that what really has to happen right here has got to be a bounce. When we really think about it, it's got to be something that's a degree 2. Now we're going to talk about this as we go into the homework. I just want you to review. If you weren't in class today, there's a couple students who weren't. As we're working through this and we find that there is a factor that's used and it's used twice, you have the ability to take that factor, FOIL it out, and use it as a trinomial, all right, and factor that out of the original equation, all right, to find the other side. That's what they're doing here, is they're finding this, and now that's a quadratic. That means that this times this gives you the original polynomial, all right? All right, so that's what it means to factor out, is that these factors, all right, give us that. That means that then you have this 3 parts that you can then use in the quadratic formula to find the imaginary zeros, the 2 imaginary zeros, one of them and its conjugate. One of them and its conjugate to get that. And then we can fully factor this out, writing it in factored form with the real 0 that has a multiplicity of 2 and the imaginary zeros that have their multiplicities of 1 each here, giving us a grand total of 4 zeros that are used. 2 of them are the same. Now, you could use the area model. In class, we also had a student who was using this as a linear factor twice and using synthetic division twice, or you could take this in its foiled out version, expanded version, and you could do not synthetic division, but long division with it. Okay, so let's jump into the homework. That's a little 3-minute recap of what we're doing. I would encourage you also to look at, what is it? Look at the notes. Here's what we wrote in class. You can pause the screen, add that for yourself. Let's move on. Let's make our answer key. Unit 2, Lesson 7. It's probably going to go over a bit, way more than 10 minutes. The graph of the polynomial function is shown. Boom. We got a polynomial. It's doing stuff. It's got 1 up, 1 down. That means it's going to be odd, okay? Identify the degree of the function and the number of real and imaginary zeros. Okay, so when I look at this, I know it's an odd degree, and I can see 1, 2, 3 zeros. I can see 3 real zeros. Now, how do we know that there would be imaginary zeros? And this is what I was talking about with one student. It's like, take this graph, take that graph, and I'm going to trace the axes. What if the axes on this, if we shifted this graph down and the axes went through it like this, we would have 1, 2, 3, 4, 5 real zeros. We'd have 5 real zeros right there. So when I shift it here and I only see 1, 2, 3 zeros, I know that there's going to be the 2 more if this were shifted. And so that means that the other 2, with this shift that's happening, are now imaginary zeros. So there's 2 imaginary zeros, and plus the 3 real zeros that we can see. Remember, real zeros we can see in the graph. That can be a strategy that we employ. We get Desmos out, we graph it, we see what it looks like on Desmos to find the real zeros. Anyway, altogether, this is telling me that it's a 5th degree polynomial. And there's the number of our real and imaginary zeros. Sorry. Let's keep going. Clearing out my workspace. focus here. So write this polynomial in standard form. Identify the zeros of the function and the x-intercepts of its graph. X-intercept. All right, so I guess not the y-intercept. So the x-intercepts are the real zeros. The real zeros. All right, so as we're looking at identify the zeros, well, it's going to have a 0 at positive 6. It's going to have so a real 0, positive 6, and 2 zeros that are imaginary. One at positive 4i for that one, and one at minus 4i for that one. Remember, taking opposite signs. Just going to zoom in a little bit more. Okay, now, how do we then write this in standard form? Well, we go ahead and multiply all this stuff together. And I'm going to take this x and, again, minus 4i and multiply it by the x and the plus 4i. I like to do this the little area model because it helps keep track of answers. You could totally just do double distributive, all right, distribute those, and then take that answer and distribute this. That's what we're going to do, but we'll do it visually. So we're going to get an x squared. When we do x times x times 4 is 4ix. X times negative 4i is negative 4ix, and these cancel out. They are 0, okay? That's nice. And what we get with this is we get a negative 4i squared. Now, whenever you have an I squared, remember, I squared is equal to the root of negative 1 times the root of negative 1. If you take the root of something and multiply it by itself, you get whatever the root was. So you get negative 1, all right? So negative 1 times negative 4 results in positive 4. So we get x squared plus 4 for multiplying these two parts together, all right? When I multiply this times this, well, now I could FOIL this out. I'm going to take an x minus 6, multiply that out. So I could do another area model. X times x squared is x cubed. All right, x times 4 is 4x. Negative 6 times x squared. Negative 6 times x squared. I wrote that wrong. It's x cubed is negative 6x squared. Negative 6 times 4. Oh my God, is negative 24. And let's see, we put that all together. I feel like I messed up somewhere here. No, my brain is glitching. Yeah. So let's see, we get x to the x cubed minus 6x squared. Yep, plus 4x, and then minus 24. I think that's all working out. That's what I got here. Answer key for this one, for number 2, is it's saying that we get this. All of you know me. You know that I make mistakes. I'm not seeing where my mistake is. Oh, I see it. 4 times 4. I'm an idiot. What's 4 times 4? 16. So we get positive 16 here. Okay, there you go. So I would be doing negative 6 times 16 and x times 16. That makes sense as to why we get that answer. Let's move on and pretend that didn't happen. All right, no, I mean, mistakes do happen, but now at least we decoded why. It was my focusing on the I squared part and the negative, then I forgot to do 4 times 4. All right, number 3, we have this. It has an x-intercept at negative 4. That means that it's going to have a factor of x plus 4 will be a factor of that. Factor it completely, even over the complex numbers. Now this is to the 3rd power, and this is one of the factors. All right, I got options here. Since this is a linear factor, I'm going to use the minus 4, and I'm going to do synthetic division. I'll take the 1, the 4, the 25, and the 100. And I'm hoping that we get a remainder 0 as we do this. Remember, we bring the 1, we get a minus 4, we're going to get a 0. Negative 4 times 0 is 0. All right, so we get 25. 25 times negative 4 is negative 100, and we get a remainder of 0. So this would be our x squared, this would be our x, and this would be, so we get x squared and a positive 25. So when we have this as a factor, our other factor is x squared plus 25. And when we look at that, can we factor that more? Well, if this was a minus, we could factor that into an x plus 5 and an x minus 5. But it's not. It's not a minus. It's a plus sign. So what we want to do is we want to take x squared plus 25 and set it equal to 0 and find the zeros for that. Well, we subtract 25, we get x squared is equal to negative 25, and then we're going to take the rooty root of that. All right. Oh, it's the root. All right, so x is equal to, the root of 25 is 5i plus or minus 5i. So there's our two imaginary roots, or along with our original one. It says factor it completely. So what would this look like in factored form? Well, we'd still have we would have f of x is equal to x plus 4, the first real root, excuse me, and the two imaginary roots. One of them is the x plus 5i and the x minus 5i, and we're done. Okay. Yeah, let's see. We skipping numbers here to number 7. If 3i is a 0 of this, find the remaining zeros, and then write f of x as a product of linear factors. Oh, I love this. Okay. All right, well, one of the linear factors is going to be an x minus 3i. Remember, these come in pairs. If we have a 3i as one of the imaginary factors, there's going to be a minus 3i as the other one. So the other linear factor would be an x plus 3i. Look at that. So we got two factors out of this. These are two imaginary ones, and I imagine that there's going to be two real ones. We got some choices here as to like how do we go about this, but I'm going to take these two as factors, multiply them, and then divide them into this. So I'm going to take x times x, that gives me x squared. Now, as we saw above here, when we're multiplying this, these conjugates here, the middle term is going to cancel out. This is a perfect square. And so we're going to get negative 3i times 3i. That is going to be minus 3i squared. But remember, I squared is negative 1. Negative 1 times negative 3 makes plus 3. 9, I did it again. 9 plus 9, a positive 9 instead of negative 3. Negative 9. Okay, this is not a linear factor. This is now a quadratic that is a factor of this. Now I have some choices. I could do long division, which is dividing that into the x to the 4th, the 5x squared, and the minus 36. Or I could do an area model. For the heck of it, I'll stick with this since I just wrote it here and divide this into it. And we go, okay, how do I get an x squared to turn into an x to the 4th? I have to multiply by another x squared. And then I multiply this into both of these parts. X squared times x squared is x to the 4th. 9 times x squared is 9x squared. That's a positive. But what we're doing with this is we are subtracting these terms. All right, so x squared minus x to the 4th minus x to the 4th is our 0. 5x squareds minus 9x squareds is negative 4x squareds. And we're done with that. Now, since this is two terms, I'm going to need two terms to work with. I bring this term down and we get minus 36. Now, what do I have to multiply an x squared by to get a negative 4x squared? Well, I'm going to multiply by a negative 4. A negative 4 times that makes negative 4x squared. Negative 4 times 9 makes negative 36. And lo and behold, when I subtract these like terms from each other, I get a remainder of 0, and we're done with that. And this is the other factor, that when I take these imaginary roots, turn them into linear factors, then actually FOIL them out and divide these imaginary factors that are nested in here, divide that into the original polynomial. I get this. And x minus 4 is the difference of squares. If I write that, that's one of the factors that gets multiplied this. I can split that up into the factors of an x and an x, a minus 2 and a plus 2. And when those multiply, the middle term will cancel out, and a negative 2 times a positive 2 will make 4. Our answer written as, so it says find the remaining zeros, write the product in linear factors. So f of x is equal to 1, 2, 3. So these 4 linear factors, look at that, adds up to 4. Great. 1, 2, 3, 64. And what are our remaining zeros? Well, remaining 0 of positive 2 and negative 2. So x equals 2, negative 2, and 3i and negative 3i. Boom, there's all of them. Okay, so that's number 7. Flippity flip. All right, we are here to number 4. It says g is a 4th degree polynomial. Okay, 4th, it's even. All right, let's look at this. The table of values is given for, ooh, thank you. You're telling me that one of the zeros is at negative 3. That means that one of the factors is going to be x plus 3. Thank you. All right, it's 4th degree. This one could be something that has a bounce. It says, which of the statements is guaranteed to be true? What we just found out is that at 1, 2, 3, negative 3, an even function, it's 4th degree. It could be facing up, both up, or it could be facing both down. It could crisscross over this, or it could bounce. We don't know that. I'm just saying that ahead of this. So G has at least 2 real zeros. Well, let's think through that. If it's a 4th degree, and it did have imaginary zeros, we know it has 1 real 0. It could have 2 imaginary zeros because they come in pairs. That would mean that it could have it, yeah, at least 2 real zeros. That's true. That's absolutely true. This could be one of the zeros, and there could be another one, or this one could be possibly squared. It could have a power of 2. We don't know that if there was a bounce. That's absolutely true. The others are not going to be true, but it says at negative 3, G has a 0 multiplicity of 2. That's not necessarily guaranteed. We're missing some information that would help us figure that out. So let's see, some end behavior or knowing what the rest of the graph does would help us out with that. X minus 3 is a factor. No, x plus 3 is a factor. That's not right. That's not right. D, the graph of G crosses the x-axis once. We don't know that. It could do a bounce and never cross the x-axis, so we don't know that. All right, number 5. Write an equation in standard form for a polynomial with zeros at 8. Multiplicity 2. Ooh, I love that. That's an x. That's an x. What is it? Minus 8. And there's multiplicity 2 squared. Great. That's a 1. And it has a 0 at, oh, if it has a 0 here at minus 3i, it's also going to have 1 at plus 3i. Hold it. Wait, didn't we already do work with this? Look at this. 3i minus, look, I am going to steal that. If those are our 2 factors, then we know that when we multiply it out, we're going to get that, an x squared plus 9. So, okay, we're also going to have an x squared plus 9. And now I need to just multiply everything out. So this takes care of the imaginary zeros. This takes care of the multiplicity of 2, the 2 of them. And so what's an x minus 8 squared? Well, that would be an x squared. The middle term would be a minus 16x, and we would get a plus 8 times 8, 64. Oh boy. All right, and we are then multiplying that by x squared and a 9. We got choices as to how we want to multiply this out. You know, you can do an area model, or you could do distributive of the x squared to everything and then the 9 to everything. Because that's just busy work at this point, and I want to keep the video short, those are the methods that we could use. Again, I could set up an x squared and a 9, x squared minus 16 and a 64. I could multiply all that out and get my terms, and combine my like terms that would happen with that. We will have 1, 2, 3, 4 parts to it. So number 5, let's see what's the answer. 1, 2, 3, 4, 5. Yeah, 5 parts to there. I feel like I messed up on something here. Yeah, and an x squared and an, okay, yeah. Yo, yeah, when we multiply this out, not everything's gonna combine as nicely as we would think on the diagonal. So we will get this answer. We're gonna move on. Number 6. Is it possible to find a polynomial of degree 4 that has zeros at 9, 2, minus 3i, and negative 7 plus I? All right, right off the bat, I'm feeling like this is a no. Why? Because anytime we have an imaginary solution, 0, it's conjugate. Minus 3i, there's going to be a 2 plus 3i. So that means that there's going to be these 2 zeros. There's a third 0, and then this one here is different than those. It's conjugate. It's going to be negative 7 minus I. That's another 2 zeros. 1, 2, 3, 4, 5. It'd be a 5th degree. All right, let's move on. Consider the last problem. Yay, consider this function. Blech. Use your graphing calculator to find any real zeros, state their multiplicity, find the remaining zeros. Okay, so if we use the graphing calculator, what we're going to see is that there is a 0. When we see this wiggly, so you open Desmos, you type this in exactly it is. 1, 2, 1, 2. We see that there's a 0 at +2 and -2. All right. That means that there are factors. Find the remaining zeros. So at -2, at 2, and there will be some imaginary zeros. So those are our real ones. There are multiplicities of... Oh, no. I'm mixing up problems. Mixing up problems. I am sorry. That's what I get for rushing. Well, we're at 20 minutes now in the video. So anyway, I am sorry. I'm looking at this and decoding what we would end up seeing on the graph if we put it in. So on a graph, we would see that this is a 4th degree, and that at -1, there is a 0, and there's a bounce there. Okay, since that is it's going to have a multiplicity of 2 because of the bounce, so it's going to be -1 is one of them with a multiplicity of 2. Writing it in factored form, that means that we are going to have this written as x plus 1, but the multiplicity of 2 gets written there, and then we're going to have more. We're going to have 2 imaginary zeros with this. Again, how do we do this? Well, let's do the area model. We didn't do the area model for this one yet. If we had this, if we FOILed it out, we would get an x squared, a 2x, and we would get a 1 if we do x plus 1 times x plus 1 itself. All right, let's see what the area model looks like. If we were to divide this stuff and find what's the top part. Okay, so x squared, we know that we have to get an x to the 4th. I'm using this information here to know that the inside stuff is this. X squared times another x squared gives me x to the 4th. So that I know that has to be on the outside. 2x times x to the 4th would be 2x to the 3rd. Okay, 2x to the, now x squared times 2x. Okay, that's what I'm doing. X squared times 1 is just 1x squared. I am going to put that 1 there as a placeholder. Now, as I set up this next part, this one right here should combine with this one to make -6x to the 3rd. So -6x to the 3rd is what we should get, but with this we're getting yeah, I'll be honest, this is going to be tough to keep track of. Oh boy, we should do long division with this. So we should be doing long division, setting this up, having our x to the 4th minus 6x to the 3rd plus 2x squared plus 26x plus 17. We could do long division with this. That's also going to be a lot. Let's use Jack's method. Take this x plus 1 and do synthetic division. All right, -1 into this, so we got a 1 minus 6 plus 2 plus 2, a 26 and a 17. What I'm getting at is that there are lots of different methods that we could use to factoring this, and I'm not going to factor this in its FOIL term. Instead, since there's a bounce, I'm going to factor this out twice. All right, remember we use the opposite number. Okay, so we'd bring this down. We got a 1, multiply, we get a -1, we get a -7, we add them together, we get a +7, 7 and 2 makes 9, multiply by -1, we get -9, 26 minus 9, and oh yeah, that's 15, right? 26 minus 9, 17. That's 17. 17 times -1 is -17. There's our 0 for our remainder. Okay, now I take and I'm going to factor out, I'm going to divide, because multiplicity 2, I'm going to divide that root out one more time. So, okay, 1 goes here, -1 times 9 is -1, -1 that makes -8. It's almost like I'm an auctioneer here. -1 times -8 makes 8. All right, 9 and 8, that's 17. -1 times 17 is -17, and we get a remainder of 0. Ooh, that's our x squared. That's our x. That is our constant. So we get x squared minus 8x plus 17. Holy moly, we get that. Now what do we do with this? We plug this into our quadratic formula and we find our roots. All right, remember the quadratic formula? Do I have sticky with it written? No, I don't have sticky with it written down. It's the opposite of the b value, so an 8, over twice the a value. 2 times 1 is 2, plus or minus the root of the b value squared. So -8 times -8 is 64. And we're going to subtract from that 4 times the a value and the c value. So 17 times 1 times 4 is 68. And look at that. We're going to get 68. What is 64 minus 68? Well, that is the root of -4. What is the root of -4? Well, it's plus or minus 2i. Okay, so we get 8 plus or minus 2i over 2. We divide them all by 2. We're going to get 4 plus or minus I. Whoo! There's a lot of work. All right, a lot of work for this. So, use your graphing calculator to find the zeros. We should be able to do that. We found one of the zeros. We saw that it was a bounce on a graphing calculator. Find the remaining zeros. That's one of the zeros. The other zero is a 2i and a, did I do that wrong? Nope, no. It's a 4. Sorry, a 4 plus I. Sorry. A 4 plus I. 4 plus I, and a 4 minus I. How do I write that in factored form? X, take the opposite of that 4, it's going to be a minus 4, and we're going to have one of them with a plus I, minus 4, one of them with a minus I. Ooh, that's a lot of work. Okay, folks. Hope this made sense. 26 minutes of going over all the homework problems. And again, what you're seeing here is employ a strategy that makes sense for you when you're factoring out. Sometimes I'm leaning towards the synthetic division. Sometimes working with these, I'm using an area model. The whole reason of teaching you lots of different models is that you can use the model that makes the most sense for you in the time. Sometimes we're doing long division. So brush up and be good to work with all of those different models. Take care. Bye.